Some of the ideas from Euler's method for solving differential equations lead quite naturally to the idea of integration, and it's going to take us a little bit to connect this up with Euler's method, but it's one of the most important topics in all of applications. And so what we're going to do for now is focus on the big picture. A lot of times when people talk about integration, they get all caught up in the details, and without the big picture, that doesn't really help you understand what's going on. And the important thing for applications is to understand what's going on. And so what we're going to end up doing is starting with a kind of an abstract problem. Now, the abstract problem is a little bit less abstract if you look at life this way. Anytime you have a product, A times B, that's an area. You have a rectangle, one dimension is A, one dimension is B. So every product that you see is in fact some kind of area. And where it gets interesting is if one of the factors starts to vary. So that's the difference between products and integrals. Integrals are an extension of the idea of products. And so the first way of looking at them is by trying to find an area. So the setup that we're going to have is this. It's pretty abstract, but it turns out to be very widely applicable. So what I'm drawing here out of your eyesight, but now I'll fix that, is the graph of some function y equals f of x. It's very important to note that f of x is greater than or equal to 0 here. And the domain goes from A to B. And so that's a pretty natural situation. And so if f were a constant function, this would just be a rectangle and we could find the area. But it is not. So how are we going to find the area that's under this curve? That's the phrase that people use, the area under the curve. Well, how are we going to do that? We know a couple of areas as a species. We know circles and we know rectangles. And so that's what we're going to do. And what we're going to do is use a problem-solving method that is widely applicable, not just in calculus, not just in math, but in all kinds of areas. And so I'm going to call this divide and conquer. This is not the only possible name that you can get for this, but here's the situation. We're going to chop the problem up into a lot of little pieces and solve the problem maybe approximately in each of the little pieces and somehow combine all those to get an approximate and then an exact solution to the problem at hand. So we're just going to divide things up and conquer them. And so we don't want to go into a lot of detail right now, but let's get into the necessary detail that we have. What's this divide and conquer thing? Well, when I was learning to fly, my first instructor told me, hey, if you need to take a big load out of a small strip, that's the thing that people get hurt doing. No, you make it a lot of small loads. As I became more sophisticated as a fly fisherman and started to fish on bigger rivers, someone gave me some really good advice, which was, it's not a big river, it's a lot of little rivers, all added up together. And so that's what we're going to do with this area problem. We're going to take this big load and split it up into a bunch of small loads, take this big river, split it up into a bunch of smaller rivers, and then approach the problem in each little piece. And so here's the deal. What we're going to do is subdivide the domain. That's the divide and conquer part. So I'll draw this in and then I'll show you what I've done. So you've got a subdivision. I've just drawn the vertical lines to indicate the subdivision. So what do we have here? 1, 2, 3, 4, 5, 6, 7 of them. And so here I've got n equals 7. There is going to have to be some notation. We don't have to get too wickety-whack and crazy about it. And the width of each of these for the moment, we're going to have each of these have the same width. In more sophisticated applications, the width varies, but for right now, we're just going to have them all have the same width. We'll call it H. Everyone loves H because it's horizontal. And just in case you feel like you need to have a formula or else you're not doing math, we're going to have that N. Oh, I'm sorry, I got this backwards because N and H look so much alike. H is a fraction. The top is B minus A. That's the size of the whole interval divided by N. So H is the size of one little subinterval. And then what we're going to do is find a height. So first we did the subdivide. That was the divide and conquer thing. And now we're going to find the height. And this is where people get all kinds of wrapped around themselves trying to figure out how to find the height. Let's just find a height. We'll worry about the exact details of how to do it later, which often don't matter in any event. So let's just find the height. So what I'm going to do is I'm just going to sample the height in each of these subintervals. So the sample is going to be this dotted blue line. That's going to be the sample height. So I'm drawing 7 dotted blue lines. There they are. They're just so dotted. They're just so blue. So the red indicates the edge of the subdivision, the subinterval, and the blue, that height is the height. So what we're going to say here is that the area in this strip right here is approximately H, that's the base, times the height, and so that's going to be the sample that we've taken there. So we call that step sampling. Most calculus books go pages and pages and pages on how to do the sampling, which in real life is, you just sample it. You just find a value. So, so I'm going to have to introduce some notation here. So the first sample, because it's the function f, I'm going to call that f sub 1. And then the second sample, I'm going to call f sub 2, and so forth and so on. And there are n of them. And so the last one is f sub n. So somehow we get some samples. In a lot of applications, the samples of the lab data let you take like every day. And so you get the first day sample, the second day sample, third day sample, whatever. Doesn't matter what when they were taken. It's just get the samples. Just sample it. Okay. So now we know that in each of these situations, let me draw kind of a blown up picture, that we've got the base at H, and then we've got the sample, and that's going to be some value of the function. I'll call that f sub I because we don't really know which one it is. And then the function's coming through, and so that's just one strip's worth. And then what we're going to see here is that there's a rectangle. Boom, 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 boom. So here's the rectangle whose area is h times f of I, and that's approximately the area under the curve over that little strip. So this is the approximation that we're going to get. And so we're going to do that in each subinterval. And so that's going to be h times f of 1 for the first one, plus h times f of 2 for the second one, plus h times f of 3 for the third one. So I'm going to call that step the sum. So that is f1 times h plus, keep going in that pattern, f sub n times h. That's our sum. And that is the approximate value of the integral. That's the approximate area under that curve. Sometimes, and this seems to happen less and less as I grow more mature in my use of mathematics. It used to be that this is all that I did, but now I tend to only sometimes have to do this. We take the limit of this as n goes to infinity. So we get a finer and finer subdivision and more accurate rectangles. And then we have a more and more accurate representation of the area. And so we take the limit and we call that the area. So sometimes we take the limit as n goes to infinity of this sum. I'll put that in parentheses, f sub 1 times h. Now this is a ton of work because for each n you would have to do a separate sample. And so usually we do a very small number of samples. For example, the TI calculators do about 100 samples. So 100 samples worked out to be a really good estimate. So that's it. Those are the 4 things that we do in doing integrals. That's the whole integration process. This is what it is. There are 4 S's to it. We subdivide, we sample, we sum, and then sometimes we take the limit. So it's 4S, subdivide, sample, sum, and sometimes. And in most applications, you only do the first 3. There are some where it's very important, if we're trying to get an exact solution to a differential equation that models something that we're interested in, then we can take the limit and get the exact solution. So that's it. That's what integration is. And there are a lot of details about how you want to do that. Okay. Notation. So the notation for this is this elongated S. It kind of looks like the F hole in a Manouche guitar or a cello or a violin or something. It's an S. S for, well, there are 4 S's here: subdivide, sample, sum, and sometimes take the limit. So there are a lot of S's. So, but we use this stylized S, kind of like in colonial times they would sometimes write S's like this. So that's when this comes from, by the way, about American colonial times. And then we indicate the interval from A to B, and then we have to say the function that we're doing this to. So that's f of x. There's no surprise there. And now comes the big kicker, is dx. So dx is bound to be a little mysterious at first. I think there are a lot of professional mathematicians who couldn't really tell you what dx is anyway. We can think of it like in the Leibniz notation for derivatives, in that the dx tells you what the variable is. So x goes from A to B. There is no x here. It's everything between A and B. And so that's what goes on with the symbol. One thing I can do just to kind of emphasize that, is I'm just going to rewrite this again, because the name of the variable is not important. So I'm going to write it as f of m dm. I've just used some color to highlight that difference. Those are exactly equal. M takes on every value between A and B. X takes on every value between A and B. But we need to have a name so that we can write out what the function is. Okay, that's what integration is. 4 steps. Subdivide, sample, sum. Maybe it's only 3.5 steps, because the last step is sometimes we take the limit. And so a lot of the stuff that we'll do with integration is filling in details here, but that's what we're trying to do. And anything that starts off as a product, if you let one of the things vary, it becomes an integral. And this enables us to work with a lot of models and solve a lot of applied problems.